This is an IMO shortlisted problem in 1993, proposed by USA. IMO competition is held annually, usually in July. Each attending country can propose up to 6 problems. There are hundreds of problems proposed every year to form a long list. Then, the problem selection committee of that year will choose about 30 problems from the long list to form a short list. Before the competition day, team leaders of all countries will choose 6 problems from the short list by voting for the actual competition. Let A, B, C, D be positive real numbers. Prove that A divided by B plus 2C plus 3D plus B divided by C plus 2D plus 3A plus C over D plus 2A plus 3B plus D over A plus 2B plus 3C is greater than or equal to 2/3. Immediately, we have 2 observations. First, the left-hand side of the inequality is homogeneous, meaning if A, B, C, D are replaced with Ka, Kb, Kc, Kd for a constant K, the inequality remains unchanged. So Ka over Kb plus 2Kc plus 3Kd, K can be cancelled. It's still the same. This gives us an opportunity, something called normalization. Without loss of generality, we can assume A plus B plus C plus D equals 4. You can use other constant instead of 4. The proof will be similar. Another observation. The equality holds when A, B, C, D are all equal. If we assume their sum is 1, then all A, B, C, and D equal 1. This gives us a hint that arithmetic mean, geometric mean inequality might be helpful. By the AMGM inequality, 1 divided by B plus 2C plus 3D plus 1 over 36 times B plus 2C plus 3D. If there's 2 terms, their sum is greater than or equal to 2 times their geometric mean, the multiplication taking square root. So that is it, exactly 1 over 6. So the sum of these 2 quantities is greater than or equal to 1/3. You might ask, why 1 over 36? Where are these coefficients coming from? The purpose of the number 1 over 36 is to keep the 2 terms of the left-hand side to be balanced. Remember the second observation. The equality holds when A, B, C, D are all equal to 1. In this case, 1 over B plus 2C plus 3D is just 1 over 6. And B plus 2C plus 3D equals 6. That's divided by 36, also 1/6. So the factor 1 over 36 is chosen so that the equality is consistent with the second observation we just discussed. Multiplied by A on the first term, the second term, and on the right-hand side. Now, the first term of the inequality is actually the first term of the original target inequality. Similarly, we can establish another 3 inequalities for the second, the third and the last terms of the original inequality. The next step would be sum up the four inequality, and the first terms of all the inequalities sum up to the left-hand side of the target inequality, and the right-hand side is simply a divided by 3 plus b divided by 3 plus c divided by 3 plus d divided by 3. Let's do it. The left-hand side of the sum up can be grouped into two parts. The sum of the two parts is greater than or equal to 4 divided by 3. And part 1, as we just mentioned, it is just the left-hand side of the target inequality. And part 2 is 1 divided by 36 plus the sum of four terms. The first term is a times b plus 2c plus 3d, and so on. This can be further simplified. For example, 1ab and b times 3a, that's 3ab, total is 4ab, divided by 36, that is ab divided by 9. Other terms are similar. There are a total of 6 terms, AB, AC, AD, BC, BD, and CD, all possible combinations. Now, we know part 1 plus part 2 is greater than or equal to 4 divided by 3. If part 2 is less than 2/3, then part 1 must be greater than or equal to 2/3. This is our target. Part 2 less than 2/3 is 1/9 plus the 6 terms less than 2/3. This is equivalent to the sum of these 6 terms is less than or equal to 6. So, we successfully reduced the problem into a relatively simpler inequality. Let A, B, C, and D are positive real numbers such that the sum of these four numbers equals 4. To prove AB plus AC plus AD plus BC plus BD plus CD is less than or equal to 6. This is easy to verify. First, A plus B plus C plus D equals 4, so the square is 16. Expand the left-hand side, we have a squared, b squared, c squared, d squared, and also 2ab, 2bc, 2ac, and so on. There are 6 combinations, all multiplied by 2, and we move this term to the right-hand side, switch the sign. Secondly, we evaluate a minus b squared, a minus c squared, a minus d squared, b minus c squared, b minus d squared, and c minus d squared. The sum of these squared is greater than or equal to 0. If we expand it and rearrange the terms, we will have the sum of these 6 terms is less than or equal to 2/3 of a squared plus b squared plus c squared plus d squared. This is not hard. You can verify it by yourself. From the equality we already established, the sum of the squares of the four numbers is equal to 16 minus this quantity. Plug it in, that's 2/3 times the whole thing. So 2/3 times 16 is 24, and minus 3 times the sum of the 6 products. We can easily see the sum of the 6 products is less than or equal to 6, as we expected. An exercise, net bit inequality. There are many different proofs for this inequality, But please follow the approach we just discussed in this video. This is a good exercise. You are going to like it. Thank you for watching.